So in the last video, we sort of introduced Bohr's atomic model, and we said that we were going to look a bit deeper into spectral lines. Before we do that, there is one important thing that I still need to explain, and that is why shells equal energy levels. So we briefly did speak about the force of attraction. If they're closer to each other, if the electron's closer to the nucleus, it experiences a greater force of attraction. If it's farther away, it experiences a slightly weaker force of attraction. Now this force of attraction manifests itself as potential energy. So this means that if I'm holding, for example, if I'm holding the pen up with my hand, and if I move my hand, the pen is going to fall because of the force of gravity, right? Gravity is pulling it down. But at this state, it's still experiencing the force, but it's not falling. So in a state like this, it is said to have potential energy. So it has the potential to fall if I move my hand. So in the same way, these electrons are held by the nucleus. They experience attraction. So they also have a corresponding potential energy because of the way the system is organized. Because this electrons here, the neutron and proton are here, because it's close enough and it's not going in, it's just being held at that constant orbit, it has an associated potential energy. Now, if it's closer together, it has a higher value of attraction, right? So typically, how it works is that for attractive forces, we use negative potential energy. It's a sign convention. The energy itself is not really negative per se. It's still normal energy. We just denote it in using negative values. So that means at an infinite distance, so if the electron's infinitely far away, then the potential energy is equal to 0. So the closer we get, the more negative we get. Let's say -1. And then if it's in the first orbit, we have a value of -13.6. So I'm using EV over here. It's just a unit, electron volt. It's a unit that measures energy. It's a little more convenient than joules when talking about these systems. So this one, the first shell, has a negative high negative value of energy, so -13.6. This one will have a slightly lower value, so on and so forth. So now, remember we said that when an electron jumps from one orbit to the other, the energy gap is sort of emitted or absorbed. So we're going to look into that a bit deeper. So if you have the first shell K, it has a certain energy, -13.6. And if you go up to an outer shell, let's say N, it has another E2. Let's say it's -4, for example. It's not really -4, but this is just an example. So the difference between this is what? -8, 9.6. So to jump from -13.6 to -4, which is, well, a higher value of energy, this amount of energy needs to be absorbed, right? Because you're going from a low energy, a super low energy, -13.6, to a slightly higher energy. This is the gap. Please check my math on this, but for now let's assume this is the gap, so that's E1 minus E2. And this energy should be absorbed by the electron to go up. Now this absorption is absorbed from electromagnetic radiation, or as you probably know it, light. Now all of this might seem a little confusing, so let's put it into an experimental context. So let's say you have a tube filled with hydrogen, right? You have a few hydrogen atoms. hydrogen, 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 hydrogen. Now what scientists did is that at a low pressure, they excited this hydrogen, so they gave it a bunch of energy. Right, so now the hydrogen started moving around really fast. And this is what happens in your neon bulbs as well. And it glows a certain color. So your neon lights, again, they only glow a specific color. So the color, of course, is the color of light, right? Color of light corresponds to a specific wavelength. So a wavelength is a property, if you don't already know it, it's a property which tells you a bit about color of light. And this is true for visible light. So that means that if you give the hydrogen energy, hydrogen atom, they get a lot of energy, then they emit a certain color of light. And the specific colors that were emitted, let's draw a bunch of lines. So let's say color 1, 2, 3, 4, 5, 6. So they observed very specific colors being emitted. This is known as the emission spectrum. And these colors that were emitted by the hydrogen atom, depending on how much energy you gave it, were known as spectral lines. So they saw that there are only fixed colors that are emitted. You don't emit any color you want. Oh, and this was passed through a prism to split it into, you can look up the experiment, but they basically passed the light coming off of this through a prism. The prism splits it up into a bunch of different colors, and they got these lines of different colors, but specific for the given atom. So by seeing how these are not continuous, which means you cannot have every color you want, you can only have very specific values of colors, they determined that electrons emit specific radiation. Again, electromagnetic radiation in the form of light. And this made sense because Bohr's model is stating that the energy emitted by an electron comes from the jump, right? Jumping between orbits, like we saw just now. So as soon as an electron up here, let's say in shell L, jumps to shell K with a certain gap, this energy is emitted. In the same way, you also have an absorption spectrum. So if you give it light and you look at what's left on the other side, you can see that only very specific colors or wavelengths of light have been absorbed. And this happens when the electron jumps from an inner shell to an outer shell. And we saw why it's emitted and absorbed, why we can't emit energy when we go up. And that's because the energy over here is higher, lower energy. And all of this will actually, in fact, set the foundation for being able to figure out what the color of light is going to be if you know where it's jumping from. And that brings us to the Redbird Formula. Just tells you what color for a given jump. So this is true for the hydrogen atom, and we're going to look at this a bit further in the next video.